So as we concluded last lecture, we said that we have already shown that the numbers pi x, x in S, is a probability for an irreducible recurrent chain, is a probability on S, if and only if there is at least one state y with a finite return time, expected return time. What we are going to show is that the very fact that when you assume that there is at least one y for which the expected return time to y is finite, what actually happens is that this property becomes true for all other states also, namely all other states. So not only is that pi x becomes a probability, but for all other states, the expected return time to those states would be finite, which would mean that all the pi's, the values of the pi's for all states x would be positive. So when pi x is a probability, it actually gives positive mass to every state x. And this will lead us to a characterization which is sort of like that we already saw that transience and recurrence cannot simultaneously coexist in an irreducible chain. In an irreducible chain, either all states are transient or all states are recurrent. Now we will get two kinds of recurrent states, ones for which the expected return time is finite and others for which it's not. What we are going to show is that these two kinds of recurrent states also cannot coexist in an irreducible Markov chain. What we have seen already that if you have an irreducible recurrent Markov chain, then the quantities pi x, x in S, where of course remember pi x is defined to be the reciprocal of expected return time. They define a probability on S if and only if there is at least one state y for which this expected return time is finite. Equivalently, that the corresponding pi y is strictly positive. So what we are going to show now, as was mentioned earlier, is that in this case what happens is actually if there is one state y for which the expected return time is finite in an irreducible chain, then this is going to be true for every other state. So this is what we will show. In an irreducible recurrent chain, if expected return time, that is Ey ty, is finite for some y in S, then it's finite for every x in S. So let's see how to prove this. So suppose we are given that Ey ty is finite for some y in S. Now note that we have seen this. For any x in S, remember the definition of z0xy, it is the count of the number of visits of a state x during time interval 1 to t1y, which is the time of first return to y. So therefore by definition z0xy is less than or equal to ty, and therefore theta yx, which is the expectation of z0y for the chain starting from y, will be less than or equal to Ey ty, which by assumption is finite. So therefore theta yx is going to be finite for every x in S. What we're going to show is none of the theta yx's can be 0. So suppose if possible, some theta yx is 0 for some x. That is the expected number of visits to y starting from y during the time interval of first return to y up to that time. The expected number of visits to x is 0, suppose, for some x. Now remember, the count of visits to x is a non-negative random variable. So the moment you say or assume that its expected value is 0, you have a non-negative random variable whose expectation is 0 means that the random variable is 0 with probability 1. So assumption that theta yx is 0 for some x in S means that for that x, py probability that z0xy is 0 is 1. Now I bring in another result that was proved earlier. So as a consequence of an earlier property of this sequence z, y, rx, r greater than or equal to 0, what we know is under any p mu, the random variables z, r, y, x are greater than or equal to 0 are IID. That is because under any p mu, the ZRX are greater than or equal to 1 are IID with common distribution as the PY distribution of Z0X. So if you take under PY, then the random variables ZRX for all are greater than or equal to 0 are IID. But we have just now seen that if you assume theta yx is 0, that implies that Z0x is 0 with probability 1. And now we are saying that ZRX are all IID for all are greater than or equal to 0 under PY. So that would mean that the PY probability that ZRXY equal to 0 for all are greater than or equal to 0 is 1. But the event that ZRXY is 0 for all are greater than or equal to 0, what does that mean? That means there are no visits to X before the first time of return to Y. There are no visits to X between the first visit to Y to the second visit to Y. There are no visits to X between the second visit to Y and third visit to Y, and so on and so forth. But that means there are no visits to X at all. So that's what I have written there. So therefore, what the fact that the probability of left side event is 0 tells you is the probability of xn not being equal to x for all n greater than or equal to 1 is 1. That means the state x is never visited for a Markov chain which starts from y. Of course, that contradicts the irreducibility of the chain, which tells us that in general every y should lead to every x. And here, since we are dealing with recurrent situation, the probability that x is visited starting from y should actually be 1. But what we have just now shown is that if theta xy is assumed to be 0 for some x, then x is never visited starting from y. So that's clearly a contradiction. So we must have that theta yx is positive for every x in S. Now, because we have assumed that for some y, ey ty is finite, we already know that for every x, we have this relationship that pi x equal to theta yx into pi y. Now what do we have? We know that pi y is positive because we are assuming that for y, and we have just now shown that for every x, theta yx is positive. So that forces pi x to be positive for all x in S. But what does that mean? That means that, see, pi x is a reciprocal of the expected return time to x starting from x. Therefore, we have proved that expected return time to x starting from x is finite for every x in x. So, the results that we have just now proved, there is a nice way to summarize this in a compact, elegant way. But for that, I'm going to make a definition, new definition. We have already defined what is known as positive recurrence, which is finiteness of the mean return time. We now define null recurrence, which goes like this. A recurrent state x is said to be null recurrent if the expected return time is infinite. Remember, it's recurrent means that Tx is finite with probability 1. However, Tx is finite with probability 1 is not the same thing as saying it has finite expectation. So therefore, null recurrence means it's recurrent but does not have finite expectation. So here's the theorem. In an irreducible Markov chain, either all states are transient, or all states are null recurrent, or all states are positive recurrent. So now we are classifying recurrent states into again two different categories, positive recurrent and null recurrent. And now what we are saying is, for an irreducible Markov chain, either all states are transient, or all states are null recurrent, or all states are positive recurrent. The second part of the theorem says that in case all states of an irreducible Markov chain are positive recurrent, in that case pi x, where pi x is given by the reciprocal of the expected return time, defines a probability on S. Part B, of course, has already been proved. In fact, it has been proved only under the assumption that there is at least one positive recurrent state. Remember, we have proved that there is at least one positive recurrent state. Under that assumption, we already proved that pi x in S gives a probability. So it's only part A which needs to be proved. But again, for part A, we already know one part of it, namely that if your chain is irreducible, then either all states are recurrent or all states are transient. That's something we already know. So what we now only need to see is that in an irreducible Markov chain, either all states are null recurrent or all states are positive recurrent. But we have just shown that. We have shown that if there is one positive recurrent state y, then all states x are automatically positive recurrent, which means that either all are null recurrent or all are positive recurrent. An important upshot of this is that in case pi x x in S is a probability on S, and we know that that happens only if all states are positive recurrent, in that case, what we have is pi x is actually positive for every x in S. So not only is pi x a probability on S, but it actually gives positive mass to every x in S. So here is a very special property of this pi x's. Either all the pi x's are 0 or all the pi x's are positive and pi x's form a probability that add up to 1. So we are now in a position to return to the questions on stationary distributions that we had asked earlier and answered the questions, at least for an irreducible Markov chain. What we will show is that if all states are transient or all are null recurrent, then such a Markov chain cannot have a stationary distribution. On the other hand, we will then show that if for an irreducible Markov chain with all states are positive recurrent, then the probability pi, representing pi x x in S, we already know it's a probability. We will show that it is a stationary distribution, and in fact we will show that it's indeed the only one. So in that case, in the last case, not only do we have existence of a stationary distribution, we also have uniqueness, whereas in other cases there are no stationary distributions. So we first formally define, I have been talking about stationary distributions because of the fact that we saw it already in the context of on and off chain, but there is a need to probably formally define it. So here's a formal definition of what is meant by a stationary distribution. So if you have a Markov chain Xn with state space S, then a stationary distribution for this Markov chain is a probability pi x x in S, such that if you take x0 to have distribution pi, then x1 would also have distribution pi. So here I'm using the symbol to mean distributed as. So a stationary distribution is a probability distribution on S, which has a property that if you take that as the distribution of x0, then x1 would also have the same distribution. Okay, so such a probability would be called a stationary distribution for a Markov chain. Well, there are other ways of looking at this definition. So suppose you denote the transition probabilities of the chain by pxy as usual. Then of course in general we know that for any y, state y, the probability that x1 equal to y can be written as the probability that x0 equal to x, and then the conditional probability that x1 equal to y given x equal to x, which is the transition probability pxy, and then added over all x in S. So essentially it's a theorem of total probability. To find the probability that x1 equal to y, you're just breaking up this according to what happens for x0. So in view of this, we can now take a relook at the definition of stationary distribution. So a probability pi is a stationary distribution if and only if it satisfies the condition that pi y is same as pi x into pxy. Why is that so? Because remember, pi is a stationary distribution means that if you take pi to be the distribution of x0, then the same pi should be the distribution of x1 also. And that's exactly what is reflected in this equation. The left hand side is pi y, which should be probability that x1 equal to y. If you take the same pi to be the distribution of x0, which is reflected in the right hand side, where pi x is in place of probability that x0 equal to x. So if a probability pi on S satisfies these equations for all y in S, then it's a stationary distribution. Of course, this is a system of equations, linear equations in pi x's. So there are S many equations in S variables. So any time you have such a thing, you can always write it in matrix notation. And the matrix notation, it looks like this, where pi is viewed as a row vector of size S, and P is the usual notation for the transition matrix. So pi equals to pi times P. Now from this last, that probability pi which satisfies this matrix equation, from this you can easily see that any stationary distribution pi automatically satisfies this. Suppose you look at pi times P to the n. You can always write it as pi times P to the n minus 1 into P. And then you can continue like that and write it as pi into P. So that would be equal to pi. Why is that so? Suppose, for example, if you take n to be 2, then pi into P square would be pi into P into P. But if pi is a stationary distribution, then pi into P is pi. So pi into P square would be pi into P into P. So that would be same as pi into P, and that gives you pi. And then by induction you get this result. But what does that mean? That means, remember that earlier we have seen that if, what is the interpretation of pi into Pn? The interpretation of that is, it gives you the distribution of xn if pi is taken as the distribution, initial distribution. So saying that pi Pn is same as pi for a stationary distribution is same thing as saying that a stationary distribution is a probability pi on S, such that if you take the distribution of x naught to be pi, then all the xn's have the same distribution pi. So it's not just x1. Automatically, as a consequence, all the xn's would also have the same distribution. So the question, of course, is, does a stationary distribution always exist? And if it does, is it unique? Well, we'll now prove a result that provides a comprehensive answer to this question, at least for an irreducible Markov chain. So what's the theorem? Suppose Xn is an irreducible Markov chain with a state space S. Part A says that if all the states are transient or all the states are null recurrent, then the Markov chain has no stationary distribution. This was stated earlier, but now we are putting it as a theorem and we are actually going to prove this. And the part B says, if all the states are positive recurrent, then this pi obtained as pi x x in S, where pi x is a reciprocal of the expected return times, that is the unique stationary distribution for the Markov chain. Now, proof of part B requires a slightly different kind of result, which is known as Sheffey's lemma. We're going to state it here without any proof. Sheffey's lemma is actually much more general. So what we're going to state here is only the required special case of the result called Sheffey's lemma. So here is the statement. Let S be a countable set, and let alpha nx x in S for all n greater than or equal to 1 and alpha x x in S be non-negative numbers. So all these numbers are non-negative numbers. And if you fix any n, look at the a and x's and add them over x in S. For every n, that sum is 1. And also these ax's, when you add them over x in S, they also add up to 1. So that's the hypothesis. Now the assertion is, if for every x in S, anx goes to ax as n goes to infinity, then what we have is sum over x in S, the absolute difference between anx and ax goes to 0, which would in particular give that the sum of anx's over x in S converge to sum of ax over x in S. So roughly try to understand what the final conclusion says. The final conclusion says, if you tell me the terms converge, that is the anx's converge to ax, then the sum also converges. But remember, in general that's not true, because the sum could be an infinite sum. AC is not assumed to be finite. So what Sheffey's lemma gives conditions under which this is true, and the conditions are, for each n the sum is 1, for the limiting numbers also the sum is 1. In that particular case also we have limit of the sum is the sum of the limits. So this is result that we are going to use for the proof of part B of the theorem. So let's now go on to the proof of the theorem. First, make a general observation, which will be actually used in proofs of both parts A and B. So before actually starting with the proofs of any of the parts, let us make the general observation. Suppose pi tilde is a stationary distribution for the Markov chain. Then we do know that for every k greater than or equal to 1 and for every y in S, sum over x in S of pi tilde x and pxy super k equals pi tilde of y. That's simply just a manifestation of the fact that if pi tilde is a stationary distribution, then it has a property that if you take x0 to have distribution pi tilde, then xk also have the distribution pi tilde. That's what is exactly reflected here. Now, of course, from this you can easily get, so look at the left hand side, add over k equal to 1 to n and then divide by n. Now, you do the same thing on the right hand side. On the right hand side there is no k involved. So if we add over k equal to 1 to n and divide by n, nothing happens. So right hand side remains pi tilde y. But the left hand side you have added over k equal to 1 to n and then divided by n. So we have one sum outside which is sum over k equal to 1 to n, and inside there is a sum x in S. But what I have done is I have interchanged the sum, two sums. But of course it is valid because the sum k equal to 1 to n is only a finite sum. So one is a finite sum, so the other is infinite or not infinite, doesn't matter. Interchange is always valid. Okay, so now this is a general observation that we're going to use later for both parts A and B. So here's a proof for part A. Recall that if all the states are transient, that's one case, then from our earlier results we already know that n-step transition probability from any x to any y goes to 0 as n goes to infinity. Okay, that we have seen earlier. Whereas if all states are null recurrent, then on one hand by the ergodic theorem we know that 1 over n summation x equal to x belongs to S, and then if you take k equal to 1 to n, pxy super k goes to pi y. Sorry, this shouldn't be sum over x equal to 1 to S. It's only sum over k equal to 1 to n, pxy k 1 over n. So that goes to pi y for all xy in S. But then pi y, because I am dealing with a situation where all states are null recurrent, pi y is the reciprocal of the expected return time. Expected return time is infinite, so reciprocal is 0 for all y in S. So in either case you actually have that 1 over n summation k equal to 1 to n pxy super k goes to 0 as n goes to infinity for all xy in S. Now suppose the Markov chain, if possible, has a stationary distribution, say pi tilde. Then from what was observed at the start, we know that this is true, that 1 over n summation x over S and then summation k equal to 1 to n pi tilde x pxy super k equals pi tilde y for each n greater than or equal to 1 and for each y in S. Now suppose I let n go to infinity. Of course on the right hand side there is no n, so let's ask what happens on the left hand side as n goes to infinity. Now notice that as n goes to infinity, for every fixed s, every fixed x in S, I know that 1 over n times the sum k equal to 1 to n pxy k, again pi x tilde y can come outside that sum over k. We know that for every fixed x in S, 1 over n k equal to 1 to n pxy super k goes to 0. I claim from that the sum also goes to 0. Of course, for that I would use dominated convergence theorem, and that applies on the left hand side because each of these quantity that we just described, namely 1 over n k equal to 1 to n pi tilde x pxy super k, that in absolute value is bounded by pi tilde x, and pi tilde x adds to 1, so it has a convergent sum. So therefore DCT applies, so the left hand side therefore would have to go to 0, and therefore one concludes that pi tilde y is 0 for all y in S, which contradicts the fact that pi tilde is a probability on S. See, in order for it to be a stationary distribution, first of all it's supposed to be a probability. But we have just now shown that in the null recurrent transient case, all the pi tilde y have to be 0. Therefore, that contradicts its being a probability. So that completes the proof of part A. Now for part B, let's fix a y. For each x in S, let a n x be this number and ax be pi x. By the ergodic theorem, we know that a n x converges to ax as n goes to infinity for every x in S. That's number one. Number two, also if I look at a n x's, add them over x in S, you can easily see that that's equal to, that sum is 1. The sum for every fixed k is 1, and then if you are averaging over k equal to 1 to n, the sum still remains 1. So the a n x's when added over x adds to 1. The ax's, of course, because positive recurrent case, the pi x's form a probability. So by positive recurrence, sum of the ax is also 1. So we have absolutely just the right conditions to be able to apply Fréchet's theorem or Fréchet's lemma. So we can apply Fréchet's lemma to get is the quantity on the right hand side in absolute value, of course, is bounded by quantity sum over x in S, absolute difference between a n x and ax, that goes to 0 as n goes to infinity. And from this we make the following observation. If I look at pi x pxy summed over x in S, that of course is equal to limit n goes to infinity summation a n x pxy. That's what has been proved just in the previous thing. Now let's write what a n x is. That's what, if I put in the value of a n x, that's what I get. Of course, again, I have made an interchange of sum over k equal to 1 to n and sum over s, but that's valid because k equal to 1 to n, that sum is only a finite sum, so there's no problem interchanging. But now if you look at inner sum x in S, pyx to the k pxy, recall that that's exactly, this is Chapman-Kolmogorov equation, that is going to be exactly pyy k plus 1. So therefore we have the final expression, limit n going to infinity summation k equal to 1 to n pyy k plus 1. Now a little bit of work and you can easily see, if we had the sum from k equal to 1 to n pyy k, then we know the limit is pi y. Now instead of k we have k plus 1, so it's actually sum from k equal to 2 to n plus 1, but you can easily verify that's also pi y, that limit is also pi y. Shouldn't be difficult. Now remember that y was arbitrary, we fixed some y, so therefore what we conclude is that from the last string of equalities, we therefore conclude that summation pi x pxy summed over all x in S equals pi y, and that holds for all y. But that exactly means that the numbers pi x x in S is a stationary distribution. So we have shown that this numbers pi x form a stationary distribution, but then we are supposed to show that this is a unique one. So to show uniqueness, let, if possible, pi tilde be any stationary distribution. As argued in proof of part A, we have this identity. This was already done in part A. Now we take the limit as n goes to infinity on the left hand side and apply dct, which applies because the same reasons as we already cited in the proof of A. And if I take the limit, it turns out the limit would be pi y on the left hand side, but the right hand side there is no n involved, so limit is the same as pi tilde y. So we end up concluding that pi y is same as pi tilde y, true for all y. That shows that any stationary distribution is just the pi y's that you have obtained. So pi y is a stationary distribution and it's a unique stationary distribution. Okay, we want to end with some remarks. For any irreducible Markov chain with a finite state space, we already know that all states must be recurrent. That we know from earlier, because in a finite state space, at least one recurrent state. So if you also assume that it's irreducible, that means all states are recurrent. Now we can now go one step further and say that indeed in a finite state space Markov chain which is irreducible, all states are actually positive recurrent. Not just recurrent, positive recurrent. Why? Because otherwise all states have to be null recurrent. But then we know that pi y has to be 0 for all y in S. That's impossible. Why? Because we have already shown that in case the state space is finite, these numbers pi x in S is a probability on S. So therefore it's impossible that all the pi y's will be 0. So that is the first remark. So the upshot is, any irreducible chain with a finite state space has a unique sectional distribution, something that we are going to use in subsequent lectures when you deal with examples of Markov chains. If we have a finite state space irreducible Markov chain, we already know that it has to have a unique sectional distribution. And of course, all states are actually positive recurrent. So that's one remark. The other remark has to do with this question of strong law of large numbers for Markov chains, a question that was raised at the beginning as a motivation for many of the other things that we did later. So we want to go back to that question and address that question. So consider an irreducible recurrent Markov chain Xn. Let f be a real valued function on the state space S. Fixing any y in S, let's define this sequence of random variables. I mean, these should ring a bell because you have already seen things which are kind of similar to this. So y0 is k equal to 1 to t1y f xk, and yr is k equal to try plus 1 to tr plus 1y f xk. So what is y0? You look at the block of time starting from 1 till the first visit to y. Look at the values of fxk for times in that block at the f values. And what is yr in general? Look at the time block between the rth visit to y, not including that, go all the way up to the r plus 1 visit including that. All the time periods in this block, look at xk, evaluate f at xk, and then take the sum. So these are random variables. Now just to give you an idea, so if you take for example f to be identically 1, then this y0, yr, etc. nothing but earlier z0y, z1y, z2y, etc. Suppose you take f to be indicator of a state x, then y0 is z0xy, and in general yr is zrxy. So you have already seen special cases of this. And we have already seen that on those special cases certain results are true about their joint distribution. Now it turns out that the same results are true for this y sequence also. So we're not going to go to the details of the proof because it's essentially very, very similar. Arguing along similar lines as was done before using Markov property, etc., etc., one can show that under P mu for any initial distribution mu, the random variables yr are varying over all integers greater than or equal to 0. They're all independent, and specifically leave out the zeroth random variable, only focus on the random variables indexed by r equal to 1, 2, etc. Apart from independence, they are also identically distributed, and their common distribution is same as the py distribution of y naught. Sort of very similar to what we had earlier seen for the zrys or zrxy's, etc. So it's pretty similar. Now, with a little bit of work, and by that I mean essentially the same kind of work that was done in the context of the zrys or zrxy's, you can do similar kind of work. We leave the details out here. One can then prove the following result, which can be thought of as a strong law of large numbers for Markov chains, and in fact has a lot of practical applications, including the well-known MCMC algorithm or Markov chain Monte Carlo. So here's the theorem. SLLL for irreducible positive recurrent Markov chain. It says that let Xn be any irreducible positive recurrent Markov chain with state space S, and let pi denote its unique stationary distribution. Then for any function f from S to R with mod fx pi x finite, you have 1 over n summation k equal to 1 to n fxk. So this is the average of the values of f at x1, x2, xn, this time average goes to the space average, which is sum over x fx pi x, space average with respect to the stationary distribution. So this left hand side is a sequence of random variables, converges to this limit which is non-random as n goes to infinity. That happens with p mu probability 1 for any initial distribution mu. So this is roughly can be thought of as a strong law of large numbers for positive recurrent Markov chains. Okay, so what we will do later are look at some examples, but let's end with this strong law of large numbers for irreducible positive recurrent Markov chains. This must have been 40 minutes. So we have already proved what we claimed in the beginning, and while doing that, in addition to positive recurrent states, we defined what are meant by null recurrent states. So they're essentially recurrent states are now classified in two categories. Positive recurrent are the ones for which not only is that the time of return is finite with probability 1, but its expected value is also finite, whereas null recurrent are the recurrent states for which, of course, the return time is finite with probability 1, but unfortunately the expected value is not finite. So this is what classifies the recurrent states in two types, and what we have shown is that just like transients recurrence do not coexist in an irreducible chain, similarly positive recurrence and null recurrence cannot coexist in an irreducible chain. So an irreducible chain is either all null recurrent or all transient or all positive recurrent, and we have talked about stationary distribution, we have proved results about stationary distribution. We have shown that in the case of an irreducible chain, when there are only transient states or only null recurrent states, there are no stationary distributions, whereas in the other case, namely when all states are positive recurrent, pi x is a stationary distribution and it's the only one. And then we ended with some remarks, and in the remarks, one thing that was important was we at least stated and gave a rough idea of what could be called a strong law of large numbers for Markov chains. So the next phase we will look at some examples.